Oi! What the heck?
Tagon.
Well, now warring nations are at it again. I can take a little bit of a break until I get my response. Oh. I'm out of Joe. Alright, problem solved. Just keep feeding my addiction. In this last video that I just made, I finally did the return volley. And I mentioned that we were going to explore a very, very interesting numerical quantity, which is not the Euler-Mascheroni constant, but sort of a complement to that if you're thinking, I don't know, like in probability or something. It's 1 minus the Euler-Mascheroni constant, or the derivative of the gamma function at x equals 2, or z equals 2. Why I want to explore this is because there are two incredibly just awesome expressions that are equal to this. One of them is an integral, one of them is a sum. And I want to explore both of those today because they are just phenomenal. And I mean just really beautiful mathematics. So I'm going to simply derive those two representations for you today, and that will be our video. So may the battle continue, Papa. Bring it the on. Because I said in the last one that I would present a novel result that I had in graph theory, which I will do, I promise. But there's one more harmonic series generalization that will stem from my previous video about the integral over the harmonic numbers that I think is even cooler than the one I just did. So that might have to be episode 15, right? Multiples of 5, baby. But I'm really happy that I've been able to get to episode 10. Here is number 11. Okay, so to do these two beautiful representations of digamma of 2, which equals 1 minus the Euler-Mascheroni constant, I need to start with for the first one, we simply need to start with the definition of the Euler-Mascheroni constant. So that is, by definition, the limit as n approaches infinity of the nth harmonic number minus the natural logarithm of n. Now, I need to sort of justify a claim that I'm about to make. So what we need to do is realize that the natural logarithm of n, I nearly wrote the limit sign, the natural logarithm of n is actually equal to the sum from k equals 2 to n of the natural logarithm of k over k minus 1. Now, why is that the case? Well, we can explore what these are. So we just have to plug in the specific values. So if we start at k equals 2, we get the natural logarithm of 2 over 2 minus 1, which is 2 over 1. And then we're adding the natural logarithm of 3 over 2. And then we keep adding forever and ever up until, not forever and ever, but up until we get to the natural logarithm of n minus 1 over n minus 2 plus the natural logarithm of n over n minus 1. Now, because of the property of the natural logarithm that if you add them all together, you can write it as sort of the natural logarithm of the product of each of these inputs, this is equal to the natural logarithm of 2 over 1 times 3 over 2 times ... up to n minus 1 over n minus 2 times n over n minus 1. And as you can see, all of these nice numerators and denominators will cancel, and we'll be left with only n over 1, which is n. And so we get the natural logarithm of n, exactly what we started with, right? So this sum version of the natural logarithm is totally valid. It completely makes sense. So because I've now justified that, I'm going to write both of these in sum form, right? SUM form. So this is going to be equal to the limit as n approaches infinity of what's the sum form of the harmonic numbers? The original one is the sum from k equals 1 to n of 1 over k minus the sum from k equals 2 to n of the natural logarithm of k over k minus 1, right? That's what we just proved that was equal to. And what I'm going to do is I'm going to reciprocate the inside, so k minus 1 over k, which will give us a power of -1 on all of those terms. But because this is the natural logarithm, I can bring the -1 down as a multiple, and we have a negative sign here, so this -1 is going to cancel with that -1, and we just get a sum, right? I hope that makes sense. And now what I'm going to do is do something a little extra, is I'm going to take the first term of the harmonic series and I'm going to put it on the outside of the limit. I'm going to remove it. So this sum is now going to start at k equals 2. So 1 plus the limit, and this is starting at 2. But now, because both of these are going from k equals 2 to n, I can combine them into one sum. I hope that's clear. So I'm just going to erase this sigma, and I'm going to write them under one sum symbol, like so. I hope that's obvious. Another cosmetic change I can do is rewrite k minus 1 over k as, since k over k is 1, I can write this as 1 minus 1 over k. But now we have the natural logarithm of 1 minus something that's always less than 1, because k starts at 2, so reciprocals of all those integers is always going to be less than 1, which means we can incorporate the Maclaurin series for natural log of 1 minus x and just plug in 1 over k for x. And so if you want to look this up or figure it out yourself, that's fine. I'm just going to roll with it and write it down. I'm just going to presume that this is a known fact. So we have 1 plus the natural logarithm, 1 plus the limit as n approaches infinity of the sum from k equals 2 to n of 1 over k minus the sum from, I guess we'll call it j equals 1 to infinity of 1 over j times k to the power of j. This is the Maclaurin series for the natural logarithm of 1 minus x, where I've plugged in 1 over k for x. So normally you'd see x to the j in the numerator, but because then plugging in 1 over k gives 1 over k to the j in the numerator, I've just put the k to the power of j in the denominator. I hope that's clear. Another cool thing I can do is realize that when I plug in j equals 1 to this, I just get 1 over k as my first term, which means I get negative 1 over k as my first term, canceling with this k. By the way, this sign change is not a mistake. The negative sign is part of the Maclaurin series of the natural logarithm of 1 minus x. 1 over k is going to cancel with the negative 1 over k that I get by plugging j equals 1 in. So what I actually end up with is 1 plus the limit as n approaches infinity of the sum from k equals 2 to n of the sum of, and I'm going to, oh, by the way, so essentially this term is going to cancel with the first term of this sum, so I'm going to start at j equals 2, and then I'm going to factor this negative 1 out. Right? I hope that's clear. So what I'm going to do is just factor this negative 1 out, because now all the terms have a factor of negative 1, and I can just write this as a double sum, right? I now have this as the sum over these terms, right? So the sum from j equals 2 to infinity of 1 over j times k to the j, right? And what this really allows us to do now is to exchange these sum signs, because there's nothing really that depends on these things. But when I exchange the sums, now the j sigma, the sigma with j as an index is going to be on the outside, which means I can factor out 1 over j, right? Because 1 over j does not depend on k. So when I rewrite this as 1 minus this limit, as n goes to infinity, I can write the 1 over I can write the j sigma on the outside and factor out the 1 over j because it doesn't depend on k, and still have the second sum from k equals 2 to n of 1 over k to the j. Right? But what does this look like? This almost looks like something very familiar. But notice, before we continue, the only thing that depends on n now is the upper index of this series, which means we can just let n go to infinity, and we'll simply have a sum from k equals 2 to infinity, right? So I can now get rid of the limit and just let n go to infinity. But what do we have if we let n go to infinity? Well, consider this sum here. If it started at k equals 1, we would just have the Riemann Zeta function of j. Zeta of j, right? But because it starts at 2, that means the first term of the zeta function, which is always equal to 1, is simply not there, which means this is zeta of j minus 1. So what we end up with is this is all still equal to the Euler-Mascheroni constant. So we now have that the Euler-Mascheroni constant is equal to 1 minus the sum from j equals 2 to infinity of 1 over j times the sum from k equals 2 to infinity of 1 over k to the j, right? This is our fact. But this right here is zeta of j minus 1. So I can rewrite this as 1 minus the sum from j equals 2 to infinity of 1 over j times zeta of j minus 1. Which means as a final result, I can conclude after subtracting 1 over and multiplying both sides by negative 1 that I get, therefore, 1 minus the Euler-Mascheroni constant is equal to the sum from j equals 2 to infinity of zeta of j minus 1 all over j. Isn't that beautiful? That's a lovely fact. There's actually something else that actually I can do to sort of make this an even cooler sum, because it's sort of annoying that this starts at j equals 2. Wouldn't it be nicer if it started at j equals 1? The problem with it starting at j equals 1 is that we'd have zeta of 1 in here, which is, it diverges, right? It's an undefined quantity. But there's something called a principal value, right? And like a Cauchy principal value. And zeta has a principal value at 1. And if you recall back, all the way back to one of my first videos I ever did on the Euler-Mascheroni constant, I showed that this limit up here can be made to equal the difference, this difference here. I showed that it was equal to the limit as a approaches 1 of zeta of a minus 1 over a minus 1. I think that's what it was, right? Which is essentially saying you're taking zeta of a and subtracting the term in its Laurent series that causes the problem, right? Because the function zeta of a has a Laurent series, but because it's undefined at 1, it has a simple pole at 1 of degree 1, right? A simple pole. And subtracting this term away gets rid of that simple pole. And I showed that it was equal to the Euler-Mascheroni constant. And that's essentially what a principal value is. If you subtract away the problem point, whatever result you get by plugging in the value where it's usually undefined, that's the principal value. So, since I'm saying that the principal value of the Riemann Zeta function at 1 is the Euler-Mascheroni constant, you could sort of think of this as 1 minus the Euler-Mascheroni constant divided by 1, right? But now if I subtract this term over, so subtracting it means I end up adding gamma minus 1 over 1, this side becomes 0. That tells me that I can put this into here because look, I have zeta of 1 in a principal value sense minus 1 over 1, which is exactly what satisfies this relationship here. Which is to say that if we did this, there is a sense in which this is true. Because zeta of j minus 1 at j equals 1 would be gamma minus 1, which is a negative number, by the way. That tells you that this whole series, if we were to allow zeta to be defined at 1, where it is the Euler-Mascheroni constant, then this series from 1 to infinity is actually equal to 0. But if we don't want to assume that and we want it to actually be well defined for the values that it actually gives us, then starting at 2 gives us the original fact that I showed you, which is that the whole series is equal to 1 minus the Euler-Mascheroni constant, which is still a beautiful, beautiful result. So I hope that that's very enticing for people. It's enticing for me, it's lovely. And I've got one more such fact to show you.